Jnanam paramam dheyam. Knowledge is supreme.
Okay, so just for completeness, I thought a couple of things I keep telling you, but I thought I'll put it on the PowerPoint today. Linear momentum operator is supposed to be related to a symmetry. What is a symmetry? I'm sure you all know. I take a cube and if I rotate it by 90 degrees, it will remain the same about any axis, right? So before I show one cube without all the vertices are identically colored, I rotate it by 90 degrees without you seeing it and I put it back. Will you be able to see the transformation? You won't be. So that is what is a symmetry. Symmetry is a sense where if you do a transformation and your system sees it as if it's an original state, then your Hamiltonian should commute with what performs that operation. Okay? What is the one which performs that operation? You wanted a translation to go from a position x to a position or an x vector to a position x plus a. And which operator helped you to do that? In a Taylor series expansion you have checked. Right? If you have not done it, please go back and check it out. You have seen that it's the momentum operator which is responsible for translating a position from x to x plus a. Okay. So this is what is the linear momentum operator which performs the transformation. Once you perform the transformation, if the system remains the same, what do we mean by in quantum mechanics or classical mechanics is that we look at the Hamiltonian and see when we take x to x plus a, whether the Hamiltonian changes or not changes. For a free particle, does it change? Because d by dx remains the same under constant translation. What happens to harmonic oscillator? Harmonic oscillator, it changes. Half kx squared you have. X shifting by x plus a will change it. Correct? So it's basically, if you take the known data, so free particle is p squared over 2m. In quantum mechanics, classical mechanics is just, if you do this transformation in one dimension as x going to x plus a, h goes to h prime, which is h for the free particle. You all agree? Translation. If you take harmonic oscillator, which is p squared over 2m plus half m omega squared x squared, that goes to h prime harmonic oscillator, which is not equal to h. And when I do this transformation, any wave function psi of x goes to psi of x plus a, and I could rewrite this in terms of e to the power of I p a by h cross on psi of x, right? This is what you have done in your assignment. It's a Taylor series expansion which I have compactly written. Sure, you have all done f of x plus a as f of x plus a times del by del x f of x and so on. And instead of del by del x, I am going to use momentum operator. Because I use the momentum operator, I will have an I and a h cross coming up. This is what you have done in your assignment. Okay. What is the meaning of this? Free particle has the translation symmetry, whereas harmonic oscillator does not have the translation symmetry. If there is a translation symmetry, the operator which performs the translation is a linear momentum. Linear momentum has to be conserved in quantum mechanics. So let me write that. So P performs translation if Hamiltonian is invariant under translation. What do we expect? H is same as H prime. Then what is conserved? Momentum is conserved, right? So this is what we call it as a translation symmetry for the system. Associated with a symmetry, the one which performs that symmetry operation will be conserved. Classical mechanics. Quantum mechanics, what do we say? d by dt, Heisenberg's picture, P operator should be 0. By Heisenberg picture, this is nothing but 1 by IH cross, P operator with H operator. Is this 0 for a free particle? Free particle, for free particle, it is 0. If this is 0, we know momentum is conserved, or matrix elements of the momentum operator does not change with time. It's a constant of motion. And this operator is the one which performs for you the transformation, which is translation. Let's do the same thing. Harmonic oscillator, you can check. What is P operator with harmonic oscillator? Will this be 0 or non-zero? Non-zero. What does this mean? It does not possess translation symmetry. So for time independent systems which we are doing, you can argue that dH by dt is trivially 0, right? Equivalently, the function psi of t, when you write, we write this as e to the minus IHT over h cross on psi of 0. So similar to what I was trying to say, x plus a is e to the I p a by h cross on psi of x. If you see x is like the parameter t, then the one which does time translation, the operator which performs time translation is the Hamiltonian, and Hamiltonian better be conserved. It's a very beautiful way of seeing it. So we can say H performs time translation. Okay. Therefore, dH of t by dt in Heisenberg picture, anyway, in any picture Hamiltonian is same, it's independent of time, you know, has to be 0. Which means time translation invariance is lost if your Hamiltonian has time dependence. So all the systems which you are studying, dH by dt is 0 because H's are all time independent. Because it is time independent, doing time translation does not affect your Hamiltonian at all. So I am just saying, see, if you want, you could put it as T naught here, and you can see this as T minus T naught, but this is a shift. So here A is the shift from what you can call it as x naught and x naught, and A is like the T minus T naught. This is delta T if you want. So every symmetry, the question is, will it be associated with the generator? S for continuous transformation, not for parity. parity is x goes to minus x. You can't write some generator for it. Some discrete transformation you don't have. For continuous symmetries, translation is a continuous symmetry, and finite translation by a vector A can be obtained by dividing into infinitesimal delta x done n times delta x, where n is very large. You can get a finite translation as n times delta x, okay, where n can be taken large and this is very, very small. Okay. So, any continuous symmetry which can be broken up into infinitesimal such transformation, you can find a generator or an operator. That's what is called as a generator of a transformation. It's called Nether's theorem. Good point. So, many of you know things. Nether's theorem in classical mechanics you have done, in quantum mechanics also it's applicable for continuous symmetries. By continuous I mean any finite transformation can be split up into infinitesimal transformation and you can add them. That's what I mean. A rotation of a cube, which I said by 90 degrees, is a discrete transformation. There I cannot apply this generator which performs that operation. On parity also you cannot apply this. But in general, for any continuous transformation, like time translation, Hamiltonian is conserved. That is an operator which generates time translation. Similarly, space translation, momentum is conserved. Momentum is the generator of space translation, and so on. Okay, so linear momentum operator is an operator which performs the translation, and a finite displacement, when we write, it is this operator always coming with what is the amount of translation you have done. Okay, so this is sometimes called as a parameter. This is the operator, and if you are in 3 dimension, you have 3 operators, px, py, pz. Similarly, you will have 3 parameters, ax, ay, az, because you have to say how much amount it is translated along x, y and z, and you get the translation operator by finite unit written as an exponential. And translation invariance of a system actually means that the momentum, linear momentum, is conserved, which we have seen in both the ways. In the Heisenberg picture, it's equivalent to saying that if a system has translation invariance, then the operator which performs translation better commute with the Hamiltonian. So, symmetries with respect to rotation, just same thing. Hydrogen atom is invariant under rotation, right? Is it invariant under translation? Hydrogen atom problem is written in relative coordinates. There is a proton at position xp vector and there is a electron with coordinate x electron vector, and when I write the V is the difference between the proton coordinate and the electron coordinate. If I shift proton coordinate by A units, if I shift electron coordinates by the same A units, which is what is called the same translation done on all the objects, relative coordinate will not change. So, you can show that it will commute. Check it. I am just trying to say this from the physics point of view. Okay. So, 3-dimensional isotropic harmonic oscillator. Isotropic in the sense its frequency of oscillation along x, y and z are the same. You can write x squared plus y squared plus z squared is r squared. That is also like a central force problem. So, in all these cases you can show that it has rotational invariance. Rotational invariance, we have been harping on this for many times in all your assignments, is equivalent to saying angular momentum is conserved, or equivalently Hamiltonian should commute with the generators which perform this rotation, which are the components of your angular momentum, and we are trying to put it in rotation in physical space, so it is orbital angular momentum. If you can understand this, this follows straightforward. but we will go over this a little slowly. So take a vector A rotated by an angle theta about any axis given by a unit vector hat n. You can take this axis to be z axis for convenience, but you can take it to be any arbitrary axis. Will the vector A remain same? It won't. It will change under rotation. But you also know that the dot product of two vectors will not change under rotation, right? Radial coordinate does not change under rotation, or any vector A dot B will not change. The reason is the rotation matrix. What is this condition called? It's called orthogonal matrices, right? R and R transpose is identity is a orthogonality condition or orthogonal matrices. R is supposed to be orthogonal matrices. Why? It has real entries only, no complex entries. If it had complex entries, then it would have become a unitary matrix. So orthogonal matrix is also a subset of unitary matrices once you put them to be real entries. Otherwise, you have to do complex conjugate and then a transpose. Since they are real entries, you don't need to do a complex conjugation. Just do a transpose. So they are also unitary matrices. And since the elements of the rotation matrices are real, the matrix is also unitary. And you can write the inverse of a rotation by an angle theta can be written as rotation by a negative angle, right? A clockwise rotation by delta theta will also be like looking at it as the other rotation by a, in the other sense as a minus. You all agree with that, right? Okay. So the explicit matrix representation, so far it is just formally writing it, but you can give a matrix representation for it involving rotation angle theta, and I am doing it about z axis for you to see this. So you can collect all these R matrices. Okay, if you take a product of this R matrix with another R matrix for some other rotation about x axis, you will get a new 3 by 3 matrix. But each of those new 3 by 3 matrix, you can show that this always satisfies this property, R transpose equal to identity. Okay. So whenever you have a collection, so this will be a set of infinite matrices you can have. You agree? You can change theta, you can change the axis, but the three axes are the three independent axes which you have. Product of any two R matrices will be a new R matrix which again satisfies this property. So the set of matrices, and we also have one more condition. What is the determinant of this R matrix? 1. The determinant of this matrix is 1. So this collection of matrices, for every matrix you also have an inverse matrix. You just have to change the sense of rotation, theta to minus theta. So this set, which is a collection of all these R matrices and which includes the inverse and the product of two R matrices, again an R matrix which satisfies this property, that is symbolically denoted, that set is symbolically denoted as a group. It's an orthogonal group, that's why they put an O, orthogonal group of rotations in 3 dimensions. So there is a 3 here. S is because we are doing proper rotation, which is determinant of proper rotation matrices are all 1. Okay. Formally they call this collection of all the rotation matrices, that set satisfies all the properties which are required. That's why the set is called a group. Otherwise you cannot call it as a group. You need a set of axioms. And symbolically this is a shorthand notation, orthogonal matrices of rotations in 3 spatial dimension, and we are looking at proper rotation collection, and that is denoted by S. S denotes determinant of these matrices are +1. So SO3 is a fancy language. If you go and see any book, you will see SO3 is the group of rotations So this is nothing but a collection of all the rotation matrices about any arbitrary axis. Okay? Don't get scared by this notation. So I'll ask you, what is SO4? The same way, set of proper rotations in 4 spatial dimension. 4 spatial you are not able to see, but suppose you think that we are in 4 spatial dimension, you will have a 4 cross 4 matrix, right? And can I talk about in 4 dimension as a rotation about an axis? So in 3 dimension, whenever you do a rotation, what exactly happens? When you do a rotation about z axis, what exactly happens? The xy coordinate of the A vector gets modified. So the one which is orthogonal to the xy coordinate, we called it as z axis. But if you are in 4 dimension, xy getting modified, there are 2 more coordinates. So you can't talk about rotation about an axis once you go beyond 3 dimensions. Okay, so we will always say it is a rotation in the xy plane, similarly rotation in the xz plane and so on, which you don't need to do when we are doing 3 dimensions. So SO3 you have all understood now is a collection of rotation matrices 3 cross 3 which satisfies RR transpose to be identical. Right? I am just trying to tell you its SO4 is again a collection of some R matrices which is 4 cross 4 with RR transpose to be identity and determinant of R is 1. Okay? That's the definition of. But why am I trying to push you onto SO4 is that if you know your hydrogen atom problem, okay, the hydrogen atom problem, you all know angular momentum is conserved. So you have angular momentum in hydrogen atom. Classical mechanics, I am sure you have all done Runge-Lenz vector, right? What is Runge-Lenz vector? They denote it by P cross L minus K R hat, something like this. It's my memory. Is this also conserved? Classical mechanics, I'm sure you would have done this in the Kepler law. So dA by dt is also conserved. If I want to put all the 6, there are 3 which are here, which is conserved. There are 3 more which are conserved. If I want to put all of them together, I need to go to SO4. SO4, as I said, it's a rotation in a plane. How many possible rotation in a plane basis you can have? Rotation about axis, there were 3 angular momentums. X-axis, Y-axis and Z-axis. In 4 dimension, if I want to look at rotation about a plane or rotation in a plane, how many independent planes are there? 6. Right? There are 6 independent rotation in a plane. So these are 6 independent parameters. I need 6 independent operators which will do. So there are 3 of them and 3 of them, they will continue to behave like I am looking at an SO4 symmetry. So we will do this if I have time towards the end, but whoever is interested can go and look at Schiff, quantum mechanics book, symmetries in quantum mechanics, where he has specifically addressed this, and you automatically, if you invoke the symmetry, you can get En to be proportional to 1 over n squared without doing any calculation. So this is something which is beautiful, that you know how much we struggle to get 1 over n squared energy by doing the Schrodinger equation, separation of variables and so on. But SO3 group can be extended to SO4. But then you will ask, what is the 4th coordinate in hydrogen atom? Right? That's the one question you can all ask. No, just take it to be an abstract P4 and an R4, like X, Y, Z, can call it as R1, R2, R3, R4, and P1, P2, P3, P4, and rewrite your Runge lens vectors in terms of the P4 and R4, and you beautifully work. Okay, like the Schwinger formalism I did to show you how to get the angular momentum J plus and J minus eigenvalues to be determined, or the coefficients to be determined, you can do this. So this has to motivate you. So what I am saying is, you wrote Li to be epsilon ijk rj pk, right? Now I am trying to say that this is not the right way to write. We will write ljk as rj pk minus rk pi pj. I am saying let's do that as a rotation in the jk plane. Okay, and now I am trying to say that we will call the actual angular momentum vectors, which you are all familiar, maybe you can use this to be tilde. Actual angular momentum is nothing but, it's your epsilon ijk, L tilde jk, where I, j and k are 1, 2 and 3. You can write your A vector as L j4 tilde, by putting a fourth fictitious coordinate. What is this? Lj4 is Rj P4 minus R4. This is where the Runge lens vector components, so this is Aj, can be rewritten. Think about it, just to kindle some of you who would like to go and look at some things. So the three generators of the angular momentum, you still can work with as if you are in 3 spatial dimension. But if you want to understand the Runge lens vector which is conserved, you can introduce one more fictitious coordinate, which is the 4th coordinate for the position as well as the momentum, and write this to be the 4 components of the Runge lens. Okay. So let me stop here